How does a computer know that a king and a queen are related, or that Paris and France belong together? It has never seen a crown or a country. Today we crack open the trick behind it all, embeddings. Here's the core problem. Computers only understand numbers, but the world is full of words, images, and ideas. To a raw machine, dog and puppy are just different strings of characters, no more related than dog and spooled stapler. We need a way to turn meaning into math. So picture a giant map, not of streets, but of meaning. On this map, every word gets a location. Things with similar meaning live close together, and unrelated things sit far apart. Dog and puppy become next-door neighbors, while stapler is across town. That map is exactly what an embedding is. Now, a location on a map needs coordinates. Two numbers give you a point on paper. But meaning is rich, so embeddings use hundreds of coordinates at once. Each word becomes a long list of numbers called a vector. You can't picture 300 dimensions, but the math treats it just like a map. Every concept has an address. Here's the payoff. Once ideas are points, closeness becomes measurable. The model checks the angle between two vectors to score how related they are. Small angle, similar meaning. Wide angle, unrelated. Suddenly, a computer can rank which sentences are about the same thing, with plain arithmetic. And the meaning captured is shockingly structured. Take the vector for king, subtract man, add woman, and you land almost exactly on queen. The directions in this space encode concepts like gender and royalty. The model was never told these rules. It learned them just by reading. So how does it learn the map? Simple. Company by keeping. The model reads mountains of text and notices which words show up in the same neighborhoods. Coffee and morning appear together constantly, so they drift close. Meaning emerges from patterns of context, no dictionary required. This trick isn't just for words. Images, audio, products, even users can all become points on their own maps. That's the engine behind recommendations and search. When a store suggests, you might also like, it's really saying, this item sits right next to what you just viewed. Let's make it concrete with search. You ask, how do I fix a slow laptop? Old keyword search hunts for those exact words. Embedding search turns your question into a vector, then finds documents whose vectors sit nearby, even ones that say, speed up a sluggish computer. It matches meaning, not spelling. But watch out for the traps. First, don't compare vectors from two different models. Their maps use different coordinate systems. Second, embeddings inherit the biases in their training text, so audit them. And third, they capture similarity, not truth. Two false statements can sit right next to each other and look perfectly related. If you remember one thing, make it this. An embedding turns any object into a point in space, where distance means similarity. That single idea powers search, recommendations, and the language models reshaping our tools. Meaning becomes geometry, and geometry is something machines can compute. So next time an app just gets what you meant, you'll know there's a map of meaning underneath. If this made embeddings click, hit subscribe for more deep dives, and tell me what concept to map out next.